So, we will continue our endeavor into the exploration of entropy. I will just remind you that where we stopped, we came to an understanding that everything can be derived due to the maximal property of the entropy. Meaning, I have this function, sum of I, fi, log of fi, which I call entropy or Shannon entropy. This is my entropy. Now, based on the maximal principle, which is similar to the maximal principle of action and similar to what we do in analytical mechanics, we only look for the extremum. We say the following: all the rules, in our case the rules are the different probabilities fi's, unknown. They can be found by looking for this extremum point. Okay? So we look for delta S, delta Fi equals to 0. Okay? And out of this, we find rules for Fi. Okay? So this is the algorithm. You start with the entropy, you look for the next room. Now, something that you need to introduce into the system in order to find the extremum point are the constraints, because the constraints can significantly modify the properties of those extremes. So, introduce constraints. Like, sum over I, fi, has to be equal to 1. Fi are our probabilities. The sum over all the different probabilities has to be 1. This is how probability is defined. Remember, we define an experiment and we and we put all the different outcomes of the experiments. We attach to all the different outcomes of the experiments some specific probability, and we normalize everything such that the probability that something will happen has to be equal to 1. So this is a very firm constraint. Afterwards, we just solve the equation and we find our rows for fi. So we did it for microcanonical ensemble, and I think I just waved my hands about how we do it for canonical ensemble. So we'll do it from scratch. Okay, so we've seen that it works for microcanonical ensemble, it works for canonical ensemble, etc., etc., etc. So let's repeat the canonical ensemble. So we know that S equals minus k Boltzmann, sum of I, fi, log of fi. We look for the constraints, and the constraints are sum over fi equals to 1. And we introduce additional constraint. The additional constraint is that we set some specific value to our average energy. Okay? We say the following: sum over of I, ei, fi equals to 1. For the microcanonical ensemble, all the energies were exactly the same. And therefore, we obtained that the probabilities have to be exactly the same for all the different states. Here, this is the additional constraint. All right, so let's see what happens. So first of all, delta S equals to delta of minus k Boltzmann, sum over fi, log of fi. Okay. We look on this as if we're performing some sort of a derivation, that we've basically taken a differential, okay, which is, in a more fancy language, a variation of the function. So what we have here is minus k Boltzmann, sum over of I, delta of fi, log fi, which is minus k Boltzmann, sum over of I, delta fi, log fi, plus fi, delta, log fi. Okay, we'll continue over here. Equals to, so we have minus k Boltzmann, sum over I, log fi, multiplied by delta fi. The delta of log fi is 1 over fi delta fi. It's just like taking a derivative. So it's plus fi multiplied by 1 over fi delta fi. And all in all, we obtain that it is minus k Boltzmann sum over I log of fi plus 1 delta fi. Okay. So this is delta S. Okay. Now, because we are going to use Lagrange multipliers, we need to take the variation also of the constraints. So we have to find the variation of this guy and the variation of that guy. Okay. So the variation of the sum, it's easy. You already seen it. So it's a delta of I fi equals sum over I delta fi. Okay. Nice. The additional part is to find the variation of sum of I ei fi. Now here it's a little bit tricky sometimes, in a sense, what we are varying. Okay? And we have to remember the following setting. We have a system, we have energetic levels or for any energies for all the different states. We are not varying the states. We are not varying the system. Right? We're varying the probabilities to find the system in different states. This is to the quantity upon which we apply the variation. We don't know FIs over here, right? But we do know what are the energies. And the energies are fixed. We're not modifying them. So when I'm looking for the variation of this guy, the only thing that varies are FIs. EIs are constant. So this is a sum over I delta of EI fi. EI are constants, so it's just sum over I EI delta fi. All in all, we have variation of this guy, we have variation of the first constraint, and we have variation of the second constraint. Okay? Now we introduce the technique of Lagrange multipliers. So it's delta S minus lambda 1 delta of sum over I fi minus lambda 2 delta of sum over I ei fi equals to 0. Okay. Now we write down the expression for delta S, for delta IFI, for delta EIFI, and we obtain that this is minus k Boltzmann sum over I log of fi plus 1 delta fi minus lambda 1 sum over I delta fi minus lambda 2 sum over I ei delta fi equals 0. Now I see in this expression that it's always the same form. I have a sum, I have some sort of an expression inside, and this expression inside the sum is multiplied by delta fi. Okay. So I want to reorganize everything such that everything will sit in one single sum. Okay. Now I want this minus k Boltzmann outside of the sum. Now in order to do this nicely, here I just pick some two absolutely random lambda 1 and lambda 2. Now instead, for this expression to be nicer, I would say, well, it doesn't matter if I pick lambda 1 or lambda 1 multiplied by k Boltzmann, and it doesn't matter that if I pick lambda 2 or lambda 2 multiplied by k Boltzmann. It's just a scaling factor. If lambda 1 is something, lambda 1 multiplied by k Boltzmann is also something. Right? So therefore I will have k Boltzmann over here, and we'll have k Boltzmann over here. Okay. Why it's nicer? Because now I can take this k Boltzmann outside of my equation and practically forget about it. Okay. So we have minus k Boltzmann sum over I. Okay. And inside I have log of fi plus 1 minus lambda. Plus, thank you. Plus lambda 1 multiplied by nothing. plus lambda 2 multiplied by EI delta Fi, and all of this equals 0. Okay. Now, I'm looking on this guy, and this is the strength of Lagrange multipliers. Overall, Fi's are somehow correlated, or more precisely, they depend on each other. Why they depend on each other? Because I have those two constraints. So they are not completely independent values, they somehow depend on each other. Therefore, this is why I use Lagrange multipliers. Because when I introduce those lambdas, I treat all the different Fi's as if they are independent parameters. Okay? Independent variables. So I have a sum. All those, whatever stands in the square brackets, are independent something. And I know that all the sum has to be equal to 0. Now, since all the different Fi's, and therefore all the different log of I plus 1 plus lambda 1 plus lambda 2, EI, all of these are independent from each other, okay? I know that log of Fi plus 1 plus lambda 1 plus lambda 2, EI have to be equals to 0. Okay? This is why I use Lagrange multipliers. Otherwise, they are somehow dependent, and then I cannot perform this step. Okay? So this is just allowed by introducing those multipliers. Okay, I have this equation, and it becomes extremely easy, right? So log of Fi equals to minus 1 minus lambda 2 minus lambda 1 minus lambda 2 EI. Fi equals to e to the power minus 1 plus lambda 1 multiplied by e to the power minus lambda 2 EI.
If the minus 1 plus lambda 1 is simply a constant.
It's a constant. It's a constant. Okay? We'll find out what this constant is. Okay. But it's simply constant. So you see that I obtained the form of the probability is a constant, because lambda 1 is some specific constant. And here I have the prefactor, which is e to the something minus something, EI. Now, I know from my previous endeavors that here it should be something like minus k Boltzmann T or minus beta EI, right? Mm-hmm. So I know this. I don't want to simply stick this beta inside. I somehow need to find that this is exactly beta, okay? Otherwise, it's not self-contained, right? So I started with a technique. I promised to you, the only thing that you need to assume is this guy and some specific constraints, and that's it. You cannot just put something by hand inside. Sometimes you can. Anyhow, how we find this lambda 1 and lambda 2? Okay, so we're going to simply introduce those guys inside our equation for the entropy. S equals to minus k Boltzmann sum over I Fi log of Fi. So let's introduce now, because we know what the different Fi's are, let's introduce those Fi's inside the formula over here. Okay. What happens? Where is my eraser? Oh. So what happens? It's fairly simple, right? So it looks like a nasty formula with those logarithms. It's just some averaging over the logarithms of the probabilities. Yeah, nasty and ugly. But little magic happens. So we have S minus k Boltzmann, sum over I. Okay, so we stick inside Fi this guy. So we have E, or you know what? We will keep it as Fi. We keep this guy as Fi. Okay? And we just replace the log of Fi with the log of this guy. So we have log of e to the power minus 1 plus lambda 1 multiplied by the power, or by exponent, e minus lambda 2 EI. Okay. So a log of a multiplication is just the sum of two logarithms. So we have minus k Boltzmann, sum over I, fi, log of e to the power minus 1 plus lambda 1. And we have plus log of e to the power minus lambda 2 ei. Okay, let's separate those logarithms and separate this sum. So we have minus k Boltzmann, sum over I, fi, and now see, instead of saying it's a log of e to the power minus 1 plus lambda 1, I just write down here minus 1 plus lambda 1. Okay. The same I do with the other logarithm. So we have minus k Boltzmann, sum over I, fi, and here I have minus lambda 2 ei. Okay, now this why I kept fi and haven't substituted for this fi this expression. You see, those guys are constant, so I can take them out of the summation. So I have minus k Boltzmann, or it's going to be k plus k Boltzmann, 1 plus lambda 1, because it's a constant. And here I'm left with sum over I fi. What is the sum over I fi?
1.
1. Okay, so we have multiplied by 1. Okay. Next thing, we have minus k Boltzmann, minus lambda 2 gets out, so we have plus k Boltzmann, lambda 2. Okay, and here we have sum over I, fi. Well, I cannot take ei out of the sum. All right. What is this sum over I, fi, ei?
U. Also 1.
U.
U?
U? It's the average of the energy, right? What is the average of the energy, the expectation? It's this probability for any given state multiplied by the value of the energy of that state. So all of this is U. So look what we got. We have S equals to k Boltzmann, 1 plus lambda 1 plus k Boltzmann, lambda 2, U. Great. Now why is great? Because, well, we have a connection between energy, between entropy and energy. There are some additional constant over here that I don't really know why and where they came from. Well, I know, but let's keep them as it is. But we know the following. What is ds to du? Here, thermodynamics comes to an aid. What is ds to du? 1 over t. Right? This is, I know, from thermodynamics. Thermodynamics. This is how we define energy, temperature at the beginning of this class. And you use this expression numerously on thermodynamics. Great. This is, I know, from thermodynamics. From my expression, what is ds to du?
K Boltzmann lambda 2.
K Boltzmann lambda 2. Therefore, I obtain lambda 2 equals to
1 over K.
1 over K Boltzmann T, which is
Beta.
beta. All right. So we do see that this part, E minus lambda 2 EI is simply e to the power minus beta EI. Okay. So Fi equals to e to the power minus 1 plus lambda 1 multiplied by e to the power minus beta EI. Okay. So this part we got right, and there is a constant. We know what this constant is. It's somehow related to the partition function. But even beforehand, we can obtain the value of this constant by looking on this expression over here. Okay. We know the following. S equals to K Boltzmann, 1 plus lambda 1, plus K Boltzmann, Lambda 2. What is lambda 2? 1 over K beta. 1 over K Boltzmann temperature. And we have U. Okay. So let's multiply everything by T. And we obtain that Ts equals to K Boltzmann 1 plus lambda 1 plus U. No. We multiplied everything by T. So where is T? Over here. K Boltzmann T.
You write 3 Helmholtz energy, right?
Sorry?
So you try to write the 3 Helmholtz energy?
No, I haven't tried. I just said what I would do if I'm a mathematician. If I'm a mathematician and I don't know physics, so the only knowledge of physics that I introduced is just by signing that ds to du it's 1 over t. That's it. Okay? So this is the physical input. The mathematical way to find the different constant is just by submit specific values into whatever I obtain. So this is how I find lambda 2. I substitute here lambda 2 and I obtain some specific expression for 1 plus lambda 1. Okay. So what is 1 plus lambda 1? Because this is the part that I need. It stands over here. What is 1 plus lambda 1? It is Ts minus U divided by K Boltzmann T. Let's rewrite it as minus U minus Ts divided by K Boltzmann T, which is minus F divided by K Boltzmann T, or beta. So you see, very nice thing. Let's put everything now inside our expression over here. Okay. We have the following result: Fi equals to e to the power minus of minus, so it's just beta f over here, multiplied by e to the power minus beta ei. So first of all, we see that there is associated thermodynamical potential, which is F is U minus Ts, Helmholtz free energy, and this thermodynamical potential is associated with the probabilities of the canonical ensemble. Moreover, you remember I had some specific partition function, which is z. Z was just a summation e to the power minus beta ei. Okay? So if you remember, Fi was just 1 over z e to the power minus beta ei. So we can compare this guy, compare this guy.
F is minus ln z over beta.
We know this expression already, right? So 1 over z equals to e to the power beta f. Ln of 1 over z equals to beta f. F equals 1 over minus 1 over beta log of z. If you go back, how we derive the canonical ensemble, you will see that expression over there. Okay? And now we obtain it from a completely different perspective by just looking on the extremum point of the entropy. Now, it's a little bit more than that. You see this constant over here, which came up as a normalization constant that stands in front of the e to the power minus beta ei. This is something that associates the specific ensemble that we use, to a specific thermodynamical potential. Okay? So there was something for a microcanonical ensemble. It was very simple. It was the energy. Okay? It was just the energy. For the canonical ensemble, we see that there is a specific associated ensemble. What is this ensemble? The Helmholtz free energy. Okay? So when we talk about microcanonical ensemble, the energy was important. When we talk about canonical ensemble, because of all of this association, the Helmholtz free energy, this is what important. Now, more than that, we have now a method, right? So those expressions, okay, are exactly the expressions of canonical ensemble that we develop by using, well, we have a heat bath, we have a temperature, we have etc., etc., etc. We use some sort of Taylor expansions, and in all sorts of things, and where we assume something about the closed environment, unclosed. You don't need any of this. You have a prescription to how to develop the different ensemble representations. Take the entropy, find the extremum when will you use the constraints. Okay? And on the way, you will find the associated thermodynamical potential. You know that what is important is the free energy. And this is what makes the connection between the statistical description by terms of partition function and the thermodynamical description that you can use in experiments or in any other way. Yes? So first of all, you know this from the canonical part, right? Now, right? So you say, I know that this guy over here is just, I can express it as 1 over z. And that's it. Then you compare whatever you have here to whatever you have there. But it's just coming from the normalization. Okay? You know the following things. Sum over fi e to the power fi equals 1. Substitute this expression over there, you obtain this again. Just coming from the normalization. Any other questions? Great. So now we are experts in developing different ensembles, right? We don't need any descriptions about whatever heat bath is, this heat bath, that heat bath. We have a method. The method we plug inside, we have the entropy, we plug inside our constraints, we do the spiel over here, okay, with the variations, etc., 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 and then you get something. Okay? Just grinding the meat. You have the grinder, you have just to apply the your arm. Okay, so let's do another ensemble. Grand canonical ensemble. Right. So what I know for grand canonical ensemble, I have to introduce the constraints, and then you will understand something about the properties of my canonical ensemble. So first of all, I say, well, I have S. This is fine. This is as any other ensemble that I have. I have an additional constraint, which is sum of fi equals to 1. This is constraint number 1. Constraint number 2, I want to say that, well, I have some specific average energy in my system. Okay. So I will introduce the following. Sum over I, ei, fi equals to where this constraint is coming from. I'm saying that the energy of my system is not constant. It can fluctuate. But I need to condition, or not condition, constrain on something, and I say, well, there is some average energy. Okay? And I will just use the symbol U. And all our examples that we did so far were just those two constraints, right? So we look on many systems, and in those systems, the system could interchange its energy due to interactions with the outside world. This is how my energy can fluctuate from one level to another. Okay? But there are also systems where it's not just the exchange of energy that happens with the outside world, but also an exchange of particles, right? there could be some fluctuations of mass. So if I'm looking on this marker, okay, and I'm asking this, well, the mass of this marker is constant, you can say, well, yes. But what happens if you look microscopically, there are some particles that attach to this marker from the air, dust and junk, and some particles that are getting expelled from the marker all the time. It's just only on average, the mass of this guy is constant. Right? There are always fluctuations of some molecules. If you look microscopically on anything, on your desk, on your hands, or whatever, some molecules are getting in, some molecules are getting out. Okay? So, in order to solve other problems, it's not enough to assume, sometimes, it's not enough to assume that my energy is constant, average. Therefore, I need to assume that, well, I have some average energy. In the same spirit, I can say, well, it's not good enough to assume that the number of particles are exactly something. It's better to assume that we have some average number. So, sum of I, Ni, Fi equals to N. You see, when I'm writing this additional constraint, I'm basically saying to you, each state now is not only defined by the energy of the state, it's also defined by the number of particles in my system at this specific state. Okay? There are exchange of energies, exchange of particles. For a given state, I would say, I'm defining the state by a specific value of the energy and the specific value of the number of particles. The fluctuations of particles can be small, they can be large, I don't really care, right? Those are my constraints. The only thing that I say to you, well, there is some specific average number of particles. It's not a function of time, because I'm assuming that my system is in equilibrium. There is some specific average function, average value for the energy. It's not a function of time, because I'm assuming that my system is in equilibrium. And this guy is always satisfied, because, well, it's part of the definition of what probability is. Okay. So, we have everything ready. Let's go for the mathematical adventure of finding variations. So we know that we need to find delta S minus lambda 1 K Boltzmann delta sigma I Fi. You see already from the start now I'm picking, instead of just some random lambda 1, I multiplied by K Boltzmann because I know that I will have to get this K Boltzmann out of the sum. Minus lambda 2 K Boltzmann delta of sum of I Fi Ei minus lambda 3 K Boltzmann delta sum over I Fi Ni, and it equals 0. So this is my equation. I need to use the Lagrange multipliers. All the different Fi's are independent. I can vary them as much as I like. And I need to find the extremum point. Alright. Now, it's easy. Once you do it once, every time to repeat it, it's actually very, very, very easy. I know what delta S is. Delta S is minus K Boltzmann, sum over I, log of Fi plus 1, delta Fi. I know what delta sum over I Fi is. It is sum over I delta Fi. I know what delta sum over I Ei Fi is. It's just a sum over I Ei delta Fi. And I also know what delta sum over I Ni Fi is. Why? Because as in the case of energies, where I assume I fix the energy of this specific state, I also here, and I'm not modifying it. Okay, the system is fixed. The same happens for the number of particles. There is a state. This state is associated with a specific energy and a specific number of particles. Those parameters are fixed and I'm not modifying them. Therefore, it's just a sum I and I delta Fi. Okay. I kick everything inside this variational equation, and I obtain the following expression. Minus K Boltzmann, sum over I, and here I have log of Fi, plus 1 minus lambda 2. I'm sorry, minus lambda 1 minus lambda 2 EI minus lambda 3 NI. I have delta Fi over here and everything equals to 0. Right? The trick is, again, while all the different Fi's are independent, why they're independent? Because I introduced the Lagrange multipliers. Thank you, Lagrange. And therefore, because the sum equals to 0, and all the different summands are independent from each other, means that it happens only when all the different summands equals to 0. So we have our equation, log of Fi plus 1 minus, oh, it's a plus, plus lambda 1 plus lambda 2 EI plus lambda 3 NI equals to 0. Log of Fi equals minus 1 plus lambda 1 minus lambda 2 EI minus lambda 3 NI. Therefore, Fi equals to e to the power minus 1 plus lambda 1, e to the power minus lambda 2 EI, e to the power minus lambda 3 NI. Great! Again, the same form. A constant. We have an exponential of lambda 2. And we're going to see that lambda 2 is just beta. Okay? And here we have lambda 3 NI. Okay? So very similar structure. Okay? And now it's just the part where we find lambda 2, lambda 3, and lambda 1. How we find this part? Well, again, by writing down the entropy. So making some sort of a connection to thermodynamics. Okay? So S is equals minus K Boltzmann, sum over I, Fi, log of I. The same trick goes, I'm substituting for Fi inside the logarithm, and I'm keeping this Fi here as Fi, because I'm going to use this properties that sum over Fi equals to 1, and etc, etc, etc. Okay. So S equals to minus K Boltzmann, question, minus K Boltzmann, sum over I, Fi. Now I'm going to do it quickly. Why quickly? Well, here what I'm going to have is as follows. Log of Fi equals to log of e to the power minus 1 plus lambda 1 multiplied e to the power minus lambda 2 EI multiplied by e to the power minus lambda 3 NI, which is just 3 logs. Log of e to the power minus 1 plus lambda 1 plus log of e to the power minus lambda 2 EI plus log of e to the power minus lambda 3 NI. It's a log of exponent of something. So this is minus 1 plus lambda 1 minus lambda 2 EI minus lambda 3 NI. Okay. So we have over here following expression: minus 1 plus lambda 1 minus lambda 2 EI minus lambda 3 NI. Hooray, hooray! Let's separate this into 3 different sums. So we have minus K Boltzmann, sum over I, Fi, 1, let's get it out already. So we have K Boltzmann, 1 plus lambda 1, sum over I, Fi. This is the first part. We have plus K Boltzmann, lambda 2, sum over I, Fi, Ei. And we have from the third part minus lambda 3 minus K Boltzmann, so it's just plus K Boltzmann, lambda 3, sum over I, Ni, Fi. What is this guy?
1.
Go over here. 1. What is this guy? U. And what is this guy? The third constraint. Just that. Here we have our equation for the entropy using the constraint and the different Lagrange multipliers. S equals to K Boltzmann 1 plus lambda 1 plus K Boltzmann lambda 2 U plus K Boltzmann lambda 3 N. Alright, now we continue our tricks. What are our tricks? We know the following thing. ds to du, we use thermodynamics. Thermodynamics. What is ds to du? 1 over t. Okay. What else do we know?
Yes, to the n is the mu over t.
Du to dn equals to
Chemical potential.
mu. Do you remember what this mu is? Chemical potential, right? Chemical potential.
So ds to the n equals to mu over t by
Yeah. But you don't need it, right? You do it step by step. So first of all, you take this guy. Okay, you take this guy. First of all, let's write down what our S is. S is K Boltzmann 1 plus lambda 1 multiplied by 1. So we have it. Let's not rewrite it. We take this guy and we write down ds to du equals to independent of u, so it's 0. Independent of u, so it's 0. Here we have K Boltzmann lambda 2. K Boltzmann lambda 2. And we know from over here that equals to 1 over t. Therefore, lambda 2, 1 over K Boltzmann t is just beta. Lambda 2 equals to beta. Nice result. Okay. Let's substitute it inside this guy. And we have S equals to K Boltzmann 1 plus lambda 1. Instead of what is K Boltzmann lambda 2 is just 1 over t, right? Plus 1 over t of u plus K Boltzmann lambda 3 of n. Okay? Now, we want to use the second term, or the second equation, which is du to dn. You're right, I know what is ds to d something. Well, I fairly cannot say that I remember properly all the different thermodynamical relations. Just remember the basic ones.
Not by thermodynamical relation, by כלל השרשרת.
Yeah, but it's easier to get it out of here. Right? So this is the definition. The moment that you have u as expression of n, it's simple. I agree with you that your way is also fine. So we have ts equals to K Boltzmann t 1 plus lambda 1 plus u plus K Boltzmann t lambda 3 n.
Without you.
With you. Okay, yeah. So u equals to ts minus K Boltzmann t 1 plus lambda 1 minus K Boltzmann t lambda 3 n. Now we can write down that du to dn equals to minus K Boltzmann t lambda 3. Equals to mu. Right? So we obtain that lambda 3 equals to minus mu divided by k Boltzmann T, which is minus beta mu. So lambda 3 equals to minus beta mu. Okay, so we found the second Lagrange multiplier. We found the third Lagrange multiplier. Let's find the first Lagrange multiplier. 1 plus lambda 1. Right? So we just take our expression for the entropy and we substitute whatever we already know. So we know what is lambda 2 and we know what is lambda 3. So S equals to, this term stays the same, k Boltzmann 1 plus lambda 1. The second term, it is k Boltzmann lambda 2. Lambda 2 equals to 1 over k Boltzmann T, so it's just 1 over T U. Right? I substituted, instead of lambda 2, this expression. Plus k Boltzmann. Lambda 3 is mu divided by k Boltzmann T, so it's just minus mu divided by T multiplied by N. Right? Okay, so what I obtained, that S equals to not S, I want to write it down. It equals to k Boltzmann 1 plus lambda 1, multiply everything by T, so T k Boltzmann, Ts equals to plus U minus mu N. So 1 O plus lambda 1 multiplied by T k Boltzmann equals to mu minus Ts minus mu N. What is this?
Gibbs canonical energy something like
Ah, yeah,
Grand
but
canonical potential.
it's going to be grand canonical potential. But this act, I take the energy and I subtract intensive variable multiplied by its associated extensive variable, and then I subtract again an intensive variable multiplied by its associated extensive variable. This is just Legendre transformation, right?
Shouldn't be a minus for
Where?
the left side?
Yes.
No, 1 ועוד lambda 1.
Oh, it's minus. Yes. So all of this, thanks. Let's call it psi. And what psi equals to? U minus Ts minus mu N. We call it the grand canonical potential. Okay. Why it's a potential? Because it's a Legendre transformation. Legendre transformation. Whenever we do a Legendre transformation to energy, we obtain some other thermodynamical potential. Okay? So this psi over here, this is our grand canonical potential. This is the potential that is associated with our ensemble. Okay? Remember, any ensemble have associated potential, thermodynamical potential. Okay? Here, we basically constrain two values. What are the values that we constrain? We constrain the energy and we constrain the number of particles. And this gave us two other variables or parameters, which was this temperature and the chemical potential. Now, I remind you, what was our expression for Fi? It was e to the power minus 1 plus lambda 1 multiplied by e to the power minus lambda 2 ei multiplied by the exponent of e to the minus lambda 3 and I. Let's try and write down everything in terms of the probabilities, okay, and define a partition function for this problem, okay? So first of all, we know the following: Fi equals 2. So we know that it is e to the power 1 minus 1 plus 1 is just divided by k Boltzmann t. So it's just f divided by beta.
Divided by beta?
Sorry.
Psi.
Why divided?
Multiplied by beta. You're right. Okay. So it's divided by k Boltzmann t. Great. Why? Because I just replaced the 1 minus 1 plus lambda 1, introduced the t multiplied by k Boltzmann, and here this is what I have. Multiplied by e. Now let's see what I have by lambda 2 and lambda 3. So lambda 2 was beta, right? And lambda 3 was minus beta mu. So it's plus beta mu and 9. Okay. So Fi equals to e to the power beta psi. It's a constant. Don't be misled by that, well, you have a psi over here, it's just some potential. That the same thing we had in our canonical expression. It's a constant. It's a normalization constant. Okay? Here we have e to the power minus beta ei minus mu and I. Now, if you don't like this constant and you like the expressions that include only probabilities and only specific values of the states, meaning energies of the state and number of particles for the specific state, I'm going to use the following thing. Well, let's perform a summation over Fi. And I know that this guy has to be equal to 1. Okay. So we do the following trick. A sum over I, let's substitute this guy over here. E to the power beta psi multiplied by e to the power minus beta ei minus mu and I. All of this equals to 1. Okay, let's take this guy out. Okay, we have e to the power beta psi sum over I e to the power beta ei minus mu and I. All of this equals to 1. Now what we've done in the canonical ensemble, if we don't have this part, what this function looks like?
Partition function.
It's the partition function. A summation of over I e to the power minus beta ei without this part is just a partition function of the canonical ensemble. So we're going to say, look, this guy is the partition function of the ground canonical ensemble. Sum over I e to the power minus beta ei minus mu and I. This is the partition function. Partition function. For the canonical ensemble, there was a simple partition function. E to the power minus beta ei. That's it. It's not the holy grail, right? Because, well, we modified the definition of what or how our system is behaving. we have an exchange of particles. Therefore, each time we exchange the particles, something happens. This something has to be accounted for, and we see that everything eventually comes down to a slightly modification of the partition function. Okay. You have to include the properties of the different states. This is how you include them. Okay. Now, so if this guy is Z, if this guy is Z, we have e to the power beta f, beta psi, multiplied by Z equals 1. E to the power beta psi equals to 1 over Z. Let's take a logarithm of both parts. So log of e to the power beta psi equals to log of 1 over Z. Beta psi equals to minus log of Z. Psi equals minus 1 over beta log of Z. This is the same definition for the free energy. Right? Remember, the free energy is minus 1 over beta. This is the ground canonical. For the canonical, it was very similar structure. F also equals to minus 1 over beta log of Z canonical. Here we can write ground canonical. The structure stays the same. The relation, the different relations to thermodynamics stay the same. Okay? But the only thing that you need to remember, and we can summarize everything, is, well, if you have a ground canonical ensemble, or basically if you have a system that can exchange particles with the outside world, you need the following: EI and NI define a specific state. You need both of them. Okay. The probability to be in a specific state, probability to be in, for a system to occupy the state number I, it is 1 over Z e to the power minus beta EI minus mu NI. What is Z? Z is just a summation over I e to the power minus beta EI minus mu NI. How is all related to thermodynamics? This is grand canonical partition function. What is this psi? Is grand canonical potential. Equals to U minus Ts minus mu n equals to minus 1 over beta log of Z canonical. Z. That's it. What we do from here? Well, you have a system, provide me a system, provide me the different states that we have for the system, meaning provide the different NIs, provide the different EIs. I know exactly how to calculate the probabilities, I know how to calculate the grand canonical potential, and then based on the probabilities, this is the connection to the partition function, and afterwards I can use the full artillery of thermodynamics to relate different derivatives of my grand canonical potential. That's it. Right? So the prescription is very simple. we will apply this specific grand canonical to ensemble to specific states. but it's more than that. We have now in our hand something that can help you to build probabilities of different systems, right? So I don't need now to explain to you, well, I have this way or that way, this canonical ensemble, that canonical ensemble, etc., etc. Provide me your assumptions about the system. How do you define the different states? Is there an exchange of energy, exchange of particles, maybe exchange of volume? Okay, so you need to define what kind of stuff your system can exchange with the outside world. What are the probable fluctuations? The number of particles, the volume is fluctuating, the energies, the magnetic flux is fluctuating, whatever do you have, right? Write this down. The moment that you have this, you have constraints, because you say, well, yes, the energy can fluctuate, but my system is in equilibrium, therefore there is some specific, independent of time, average value of the energy. My magnetic flux can fluctuate, right? But on average it stays the same because my system is in equilibrium. Write down all those constraints, use the definition of the entropy, perform whatever we have here, basically solve the variational equations. They are always simple to solve, it's always the same thing. And then you will obtain your definitions of probabilities, your partition function, and the connection to thermodynamics, basically the thermodynamical potential. And you can have infinite number of different thermodynamical potentials because it's always some sort of a Legendre transformation of your energy. Okay? So this is the big connection between entropy, Legendre transformations, energies, and the different probabilities. Okay? You can have whatever ensemble do you want. We usually use canonical and grand canonical because they all are applicable for the examples that we solve. But you can invent your own system, derive your own ensemble representation, and your own definitions of probabilities. Great. Where we are going to, any question about this? Okay. So either I'm really, really, really far above you, or you're extremely smart. I vote for the second part. Okay, so the applications. Applications, quantum gases. Now, the problem with application is, well, you see there is a connection. So the moment that you know the partition function, you know the grand canonical potential. And from the grand canonical potential you can compute whatever you like. You're just taking different derivatives, right? It's just remembering what is the derivative with respect to this variable, that variable means. That's it. Okay. So the crucial part is the computation of the partition function. It was the hard part for the canonical ensemble, and then also the hard part grand canonical ensemble. But actually, sometimes we use grand canonical ensemble in order to simplify systems of canonical representation. Okay? So if you remember, the main problem was in canonical ensemble is the moment that we have interactions between different particles, we are somehow doomed, right? So I told you, and this is what we've done so far, is the only way that we can represent particles or solve problems in canonical ensemble is by somehow turning the system effectively to be a system of independent quasi-particles. Those quasi-particles can be whatever. We've seen phonons, we have waves, we have specific monomers, etc., etc. But there are always some effective representation in terms of non-interacting particles quasi-particles. Okay? There is also an additional way by saying, well, I have a system with canonical representation, okay? And the interactions are very strong such that I simply cannot find an effective free particles, okay? The thing to do sometimes, and we will see it specifically in the case of quantum gases, is to say that, well, the number of particles can fluctuate. So the grand canonical ensemble have two nice things about it. First of all, well, yes, it's indeed describes systems where the number of particles can fluctuate. But second, it's the moment that we ease this assumption that the number of particles can fluctuate and it's not constant in time, we can solve specific problems that are related to quantum cases. Okay? Why? So you all know that in quantum world, well, it's in some way it's similar to our world, but in some sense it's very, very, very different. Okay? So if I'm looking on any system that I can imagine in classical world, and I say, well, those two particles are not interacting. You can say, well, it's a stupid idea. But I say, well, whatever. They do not interact with each other. All right? In quantum world, I cannot say that, right? Because in quantum world, I have a Pauli exclusion principle. What it means?
So the exclusion principle that certain particles have symmetry or anti-symmetry to one another depends on their type.
And the outcome?
Two fermions cannot occupy the same quantum.
Exactly. If I have, so the particles related to the symmetrical or anti-symmetrical properties of their wave function, okay? So we have bosons and we have fermions. Bosons, they don't care about each other, so it can be exactly the same state. Fermions, those would be the anti-symmetry in their wave function. They cannot occupy exactly the same state. Okay? So if the only thing that defines my system is my energetic spectrum, okay? Let's assume it's a very stupid system where I only have energies. Okay?
So this is the only quantum number you have.
I have only one quantum number, so those are my different states. Okay? The Pauli exclusion principle says the following thing. If I put a fermion, let's say an electron, over here, okay, I cannot put another electron, and this arrow says that it has a spin up, or spin plus 1/2. I cannot put another electron at the same level. Right? This is not allowed. Okay? So if I want to describe something about the quantum world, I always have to make this separation. If I have fermions or I have bosons, the moment that I have fermions, I cannot simply say, well, they are not interacting. Okay? I can have electrons, I can forget about the interactions, I can forget about the Coulomb law. Okay? I can forget about all of those guys. But I cannot forget about the Pauli exclusion principle. I cannot kick it out of the system. This is something that very deeply defines what is the quantum world for fermions. Therefore, the interactions is extremely strong. Extremely strong. So if I have a system of different electrons, okay, and I need to write the partition function, okay, and I need to write the partition function, I need to always keep in mind, well, is this state is occupied, how it's occupied, etc., etc., etc. Okay? So when I'm writing a partition function, okay, I need to understand where I already put my particles, where I haven't put my particles, and etc., etc., etc.
So you need to have a memory.
No. The problem is the constraint, right? So if I have exactly two particles in my system, okay, so I need to understand if I put here already one particle, okay, and I have two particles in total in my system, right? So the other particle can only be over here, or over there, or over there. Okay? So it's a problem. Okay? It's very similar, if you remember, it's very similar to the microcanonical ensemble. What was the problem with the microcanonical ensemble? Fixed total energy. Okay? The moment that I have fixed total energy, and I need somehow to separate everything to different states, okay, the particles, different boxes, and I remember that the total energy is constant, okay, it influenced in such a way that I had a hard combinatorial problems. The same happens over here. The moment that I have this strict constraint, and it's not a constraint about the average, the constraint here is about the total number of particles and the interaction. So if I put something in this box, the other guy cannot be in that box, it can be somewhere else, and I have to think about it all the time. Okay? This is why we introduce the fluctuating energy in the canonical ensemble. The same goes for the grand canonical ensemble. If we work with constant number of particles and we have very strong interactions, we're doomed. Okay? It's a really hard problem to solve when you constantly have to keep this constraint. The number of particles is exactly this and that. But if you free this assumption, you just simply say, well, I don't care about the total number of particles. Instead, I have average number of particles. Like here, I have average energy, and I have average number of particles. Things are going to be much, 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 much easier, right? So this is what we are going to do right now. Okay? And you will see that the moment that I'm using this grand canonical ensemble, and I'm allowing for fluctuations of different particles inside my system, I don't have to keep track. Is it occupied, and what else where else can I put my particle? Okay? So my simple system is as follows. I have simple example. I have three energetic levels, okay? And I have non-interacting fermions that can have a spin 1/2 or -1/2. Okay? So I have epsilon 1, epsilon 2, and epsilon 3. So I have three energetic levels in my system. That's it. And I want to use grand canonical ensemble. Canonical ensemble. And I want to write down the partition function. Okay, the grand canonical partition function. Okay. And out of this, maybe to see something about what happens in the system. Now remember, eventually my goal is not just simply write down the grand canonical function. It's also to say, to show to you that it can be factorized. Okay? Remember, the only way that I know how to solve anything is just by using some sort of factorization. I cannot use this factorization because if the number of particles is fixed, they affect each other all the time because of the Pauli exclusion principle. Therefore, I'm trying a different approach. Instead of trying to create effective particles that I can't, I'm trying to say the following. I will ease my assumption about constant number of particles. I have fluctuations of particles. Okay, so let's assume that electrons can come out, can get out, can get in, etc., etc., etc. Okay. So how we do it? You write down the grand canonical partition function in the same way as you write down the canonical partition function. So Z, grand canonical, equals to sum over I, e to the power minus beta, ei, minus mu, and I. So we basically need to look what is this EI minus mu NI. Okay. So I can do this in two different ways. One way is just to picture all the different possible realization of my system. So I have epsilon 1, epsilon 2, epsilon 3. And let's assume now that, for a second, that the spin is always 1/2. 1/2 plus 1/2. We'll treat a little bit later what happens when we have this degeneracy of 1/2 and minus 1/2. Okay, now I have to count all the different states. So I put one particle over here, I put one particle over there. This is a specific state, okay? Or I can have the following state. I put one particle over here, and I put one particle over there. The energy that is associated with this state is epsilon 1 plus epsilon 2. And the number of particles that associated with the state is, so epsilon, let's call it I, and Ni equals to 2. For the state, it's epsilon j. It's going to be epsilon 1 plus epsilon 3, and j equals to 2. And I have to go over all the different configurations where I cannot put my different particles, right? I have to count all the different states, etc., etc., etc. Now, it's a problem. Why it's a problem? I have to keep in mind, well, where I put the particle, where I haven't put the particle, etc., etc. So what are the different stories that I try to pump into you? Well, oh, it's going to solve everything, this canonical ensemble. Well, the thing is, this specific property of fermions can be used extremely nicely in order to write down the different energies. I'm going to say to you the following thing. So what is the energy of the system? Let's write it down. It is epsilon 1 plus epsilon 2 plus epsilon 3. Okay? But it's not always just epsilon 1 plus epsilon 2 plus epsilon 3. Write this down, so it is going to be n1 and n2 and n3. What is n1? So it is 1 epsilon 1 is occupied, and 0 not epsilon 1 not occupied.
Stas?
Yeah?
Why can't two particles occupy the same state?
Because they are fermions.
But if they have opposite spin?
No, I told you that they have exactly the same spin.
Okay.
I will treat the degeneracy a little bit later. Okay? And n2, it is the same. 1 and 0, epsilon 2, occupied, otherwise. And I'm saying the same thing, n3 is 1 or 0, epsilon 3, occupied, otherwise. So basically, I invented occupation numbers. Now I know, because those are fermions, either I have a particle in this state, or I don't have a particle in that state. That's it. Okay. Now moreover, I can write down Ni in the same way. N is just N1 plus N2 plus N3. Okay. So write down the following thing. EI minus mu Ni, it is N1 epsilon 1 plus N2 epsilon 2 plus N3 epsilon 3. With specific values for N1, N2, and N3. Minus mu N1 plus N2 plus N3. In total, write it down as EI equals to N1 epsilon 1 minus mu plus N2 epsilon 2 minus mu plus N3 epsilon 3 minus mu. So when I write down the grand canonical function as a sum over all the different states, what are my different states? The different realizations that we have over here. E to the power minus beta n1 epsilon 1 minus mu multiplied by e to the power minus beta n2 epsilon 2 minus mu multiplied by e to the power minus beta n3 epsilon 3 minus mu. Right? And then I have to sum over all the different states. But what is summing over all the different states? It's just summing over all the possible values of n1, n2, and n3. Do n1, n2, and n3 depend on each other? The answer is no. n1 is either 0 or either 1. It doesn't care what happens to epsilon 2 and epsilon 3. So when I'm using this representation, I have created not different particles. I'm looking on the independence of different states. Right? And this can be done because the total number of particles is not constant. Only in this way I can use this. Right? So this guy equals to a sum over n1, e to the power minus, and a sum over n2, and a sum over n3, e to the power minus beta n1 epsilon 1 minus mu, e to the power minus beta n2 epsilon 2 minus mu, e to the power minus beta n3 epsilon 3 minus mu. Okay, but n1 independent on n2, n2 is independent on n3, etc., etc. So I have sum over n1, e to the power minus beta n1 epsilon 1 minus mu, sum over n2, e to the power minus beta n2 epsilon 2 minus mu, sum over n3, e to the power minus beta epsilon 3 minus mu. Look, factorization. This is what we've been looking for. So I can write it down as z1 multiplied by z2 multiplied by z3.
Wait, you wrote this
3 times. Yes, what's the...
z1 multiplied by z3.
Ah, z2. It's my way of writing 2. Now, if they're independent, that's it. I solved the problem, right? I just treat any state independently of each other's, of the others, and that's it. Now, this I've done, z equals to z1 multiplied by z2 multiplied by z3. What would happen if I now add the degeneracy that all the different particles are not restricted to just spin plus 1/2, they also can have a spin minus 1/2. What happens when I introduce this degeneracy? Well, whatever happens is that I can separate now to n. Well, we have n1, n2, plus n3. But n1, I can say, well, I count separately particles with spin up, plus 1/2, and I will count separately particles with spin down. Right? So when I do this, I will get that z is going to be z1, because I only count particles at point with plus 1/2. I have this time over here, but the same will happen for Z1 with spins that are going down. The same will happen for Z2. This spins up, and Z2 spins down, Z3 spins up, Z3 spins down. And if you look on what is Z1, Z2, or Z3, this is Z1, this is Z2, and this is Z3. Does it depend on the spin? It's not depending on spin. It's independent of spin. Great. Z2 is independent of spin. Z3 is independent of spin. So I don't care about this spin over here. Okay? So what I'm getting is that partition function is just Z1 to the power 2, and Z2 to the power 2, and Z3 to the power 2. So the degeneracy, right? The state, what is a spin? It's a degeneracy of the system. Right? The degeneracy comes into the power of this. Why? Because I can separate it in two different systems. Spins with 1/2, spins with minus half. They do not interfere because I can represent the total number of particles when I'm counting only halves and minus halves. I can introduce further up, +1/2, +3 halves, +5 halves, etc., etc., etc. And it will only eventually generate this degeneracy of the partition function. That's it. So what we have managed to obtain over here, when we look on the systems of fermions, the partition function is just a multiplication, a factorization of different partition functions of different states. What is independent, not the particles are independent. The particles affect each other because they're always a Pauli exclusion principle. But when I'm using this ground canonical representation, I'm taking advantage of the fact that the number of different particles is not fixed. It can fluctuate. Therefore, I can construct this independence of different states. Not particles independent, states independent. These as the partition functions that describe not the behavior of single particle. They describe the behavior of single states, and the states don't care about each other anymore. Okay? The moment that I have some sort of factorization, everything else comes out very nicely. I won't have the time to describe to you everything, but what we are going to do now is just to explore the partition function of a single state. Z1, partition function of single state. Everything will be described, as we see from this factorization, everything is going to be described by the behavior of this partition function. It's not a very simple partition function in a sense, as we know. It depends on many different things. What is Z1? Let's just write it down over here. So Z1 is sum over N1, e to the power minus beta, epsilon 1 minus mu. Oh, I'm sorry, there is a beta N1. Now N1 is 0 or 1. So Z1 is either e to the power 0, so it's 1, plus e to the power minus beta, N1 equals to 1, epsilon 1 minus mu. So the exploration of this simple function, and it's indeed a simple function, okay, it's going to explain all the behavior of fermions, and as long as we assume that they are independent. And we'll also tell you how it's somehow related to a sigmoid function, which is constantly used in AI nowadays, and etc. Right, so we'll all see you next week. Happy Hanukkah.
Thank you.
כן, אני באוטו.
לא משנה.
זה כתוב לך. אני ראיתי את זה כתוב לך משהו.
כן, אחד שווה אחד ועוד.
המחלקה למתמטיקה התלוננו עליו. אשכרה אני חושב שזה גם יותר הוגן להתכוון על מרצה, כי הוא רוצה ללמד אותך יותר, הוא לא רוצה לעבוד יותר, אתה אומר לו